Hi, my name is Samantha Melinda, and today I'll be talking about the 7 types of quadrilaterals. Now, a quadrilateral is just, it means 4 sides. That's what the prefix of quad means. Therefore, any shape with 4 sides is considered a quadrilateral. Now, we'll be talking about the 7, which are identifiers. They have specific properties that we will talk about. And they also have a lot of different properties and a lot of the same properties. So here's the family tree a lot of people know and see. As you see, the quadrilateral is the primary qualification for these shapes. Therefore, they all have 4 sides. We know that's a quadrilateral. And the ones that branch off of this family tree are more specific. You have the first one, which is 2 parallel sides. This incorporates a trapezoid and an even more specific trapezoid, which is an isosceles trapezoid. Then you have the 2 pairs of parallel sides, which in general means a parallelogram, and then gets more specific to a rectangle, a rhombus, and a square. And then the last one has no parallel sides. It is a kite. So again, these all go in the category of quadrilaterals. Then you have your trapezoids, which are 2 shapes. Then you have your parallelograms, which is 4 shapes. And then you have your kite, which is 1 shape. So they all kind of go in their own little groups. Then you have the history. Now, I will warn you, there's not a lot of history on quadrilaterals. We know that the Europeans or the Greeks really liked quadrilaterals, or not quadrilaterals. They really like geometry. So this kind of stems from that. Quadrilaterals were actually first discovered by the ancient Greeks when they invented it with only 3 sides. Now, that doesn't really go with the given name that we know today, but we know that they had an idea of what a quadrilateral was. They just were more stuck on the triangle per Pythagoras and the Pythagorean theorem and so forth. But then this changed when the Romans decided to add the 4th side and created the different types of quadrilaterals that we see today and that I showed you in the previous slide in the family tree. Now, if you wish to single out an earlier contributor, it would be the 9th century Indian mathematician Mavarya. He divided quadrilaterals into the 5 different classes, those with unequal sides, all sides being equal, opposite sides being equal, 2 opposite sides being equal, and 3 sides being equal. So he really focused on the congruency of side lengths, rather than like the parallel sides or what the angle measures were or the diagonals. He didn't really get as specific as that, but this was a great start because, as we know, some of the very key features of some of these parallelograms are their side lengths and the congruencies of that. So this was a great start to the ideas of quadrilaterals. The first quadrilateral we're going to talk about is the parallelogram. And as we said, this is a more general idea, and we're going to go into 3 more specific ideas of parallelogram, which is a rectangle, a rhombus, and a square. So this is a little more general, and all these properties that we're going to talk about also relate to those 3 shapes. Those 3 shapes, again, are just more specific. So any properties that I say here should be understood for those 3 also. So we have the parallelogram, and there's a picture on the bottom. A parallelogram is a quadrilateral, specifically with parallel opposite sides, and angles made by each opposite side are also equal. So let's talk about our properties. Opposite sides are parallel and equal. They are shown on the picture by the arrows and the straight lines. And by color, opposite angles are equal. Those are shown also on the picture. Everything's going to be shown on the picture. So again, those opposite angles are equal. The sum of 2 consecutive angles is 180. Consecutive angles means either the top 2 angles, the bottom 2 angles, the left and right angles, and the left angles and the right angles. So they are actually on the same line. They are not opposite. If you add those together, you should always get 180. Diagonals bisect each other. That means perfectly splitting the diagonals in half. And each diagonal bisects the parallelogram into two congruent triangles. So these are the same triangles. They are congruent. And these are talking about the bigger triangles. As you see, there are 4 triangles within the parallelogram, but we are looking at the triangles created by 2 of those triangles. So there's one in the top left, there's one in the bottom right, and then also turned. And then you have the equations for area and perimeter. Those equations don't really change too much with quadrilaterals, but we will see some differences in the more specific ones. So let's talk about an example of how we would use these properties to, if we notice a parallelogram, how we can use these properties to solve for missing variables, missing side lengths, or even missing angle measures. So for this one, we are actually trying to find the values of x and y. We know this is a parallelogram because the 2 opposite sides are parallel. That is shown by the arrows. And so that means the opposite angles are congruent. As you see, we are given 4 angle measures, but 2 of the angle measures have variables that are missing. So because the opposite angles are congruent, we can create some equations. So our first equation is the 2x plus 40, which is in the bottom left-hand quarter, and the 70, which is in the top right. We are going to solve by minusing 40, then divide by 2, and you'll get x equals 15. Now, if I ask for the angle measure, you just plug that in to 2x plus 40 and get the angle measure. You will do the same thing with 5y plus 15 and equal that to 110 because they are opposite angles. Subtract 15, divide by 5, and you get 19. So that's one example. Again, keep in mind there are many examples for a parallelogram, but this is just one of them. Now let's go on to a more specific parallelogram. You have a rectangle. It is a type of parallelogram with a little difference in the angles of the sides. So our first property, again, opposite sides are parallel and equal, which is a parallelogram. Each interior angle is a right angle. That is specific to a rectangle. The diagonals bisect each other and have the same length. And then there are the equations again for the area and perimeter. So let's look at an example for this one. As you see, we have the diagonals and we have the side lengths. We are given some information there, and we want to solve for x and y. The diagonals bisect each other, so that means we know D to E is equal to E to B. So we can equal those 2 equations together. We subtract 6, divide by 2, and we get x equals 15. Again, that is given from the property of diagonals bisect each other. Then we have the opposite sides, AB and DC. They are equal because they are opposite sides. That is a property. So we can do 2y minus 6 equals 12. Add 6, divide by 2, and you get 9. So we actually use 2 different properties in this one. Now let's look at a square, even more specific parallelogram. They have equal sides. That's specific to a square is that all sides are equal and also every angle is a right angle like we saw in the rectangle. So all 4 sides are equal. We show that with all 4 being blue lines, and they are still parallel because they are a parallelogram. The measure of each interior is 90, just like the rectangle. The diagonals are equal to each other, but they bisect in a right angle, which is cool. And then you have your equations for the area and perimeter. So again, we're getting more specific with parallelograms. So we are given our square. As you see, we have our diagonals of 2y and 10. Knowing that the diagonals bisect, we can equal these. So we get 2y equals 10, divide by 2, and we get y equals 5. Now, this one's a little different. We know that they bisect each other. Therefore, we can say these are alternate interior angles because QR and PS are parallel lines, and then you have the separating line there, and therefore 5x and 3x plus 18 are alternate interior angles, which you might not remember are congruent. We can equal those two, minus the 3x, and then you get 2x equals 18, divide by 2, and you get x equals 9. So that used a property, but we also had to have prior knowledge of alternate interior angles, but that was a little challenge for you. Now let's look at a rhombus, another specific parallelogram. It has equal sides, but no right angles. So the square is actually the most specific. The rectangle is the one with right angles. The rhombus is one with equal sides. And then those kind of combine to get a square, as you saw in the family tree. The properties are all four sides are equal, shown on the picture. Opposite angles are still congruent. The diagonals bisect each other at right angles and intersect the interior angles. And again, just to repeat so we understand this, the sum of two adjacent angles are equal to 180. And we stated that in parallelograms, which is comes to our rhombus. This equation is a little different. The area, it's 1/2 the sum of the length of diagonals, which is a new one. So let's look at our example. Given the rhombus, use the properties to solve for the missing variable. We know that the diagonals bisect each other. Now, you might be asking, oh, so we do x equals 8. No, they're not on the same diagonal, so we cannot do that. But we do know it creates a right angle, making 17, 8, and x a right triangle. And we know a great equation that helps us with a right triangle with a missing side, and that is the Pythagorean theorem. So we can make 8 squared plus x squared equals 17 squared. We simplify those squares, subtract the 64, we get x squared equals 225, and when we square root both sides, we get 15. And again, we're just doing positive 15 because negative 15 does not make sense. Let's do the kite. This is not a parallelogram. We are away from parallelograms and going into the kite. A kite is a quadrilateral with no parallel sides. There are two pairs of sides of equal length that are adjacent to each other. So the one that makes the top of the kite and the one that makes below the bottom of the kite are congruent to each other. So two pairs of adjacent sides are congruent, shown with the lines. One pair of opposite angles. These are the angles that are created by the two different length sides. An axis of symmetry right through the long edge, the long side. And then the two diagonals are not of the same length, but they do create a right angle. You have this equation. The area is actually very similar to the rhombus, which is an interesting little connection. Let's do our kite example. So we have our kite. We know the adjacent sides are equal to each other. So those are the first two sides that make the top of the kite. So that z equals 3. And then the bottom two sides that make the bottom of the kite, which is y equals 7. Then we know the opposite angles created by the different length sides are congruent. So we can do 3x plus 4 equals 112. Solve by minusing 4, dividing by 3, and you get x equals 36. So just remember that they are not parallel. That's what makes it a kite. But the adjacent sides are congruent. That's a good little idea. And let's talk about trapezoid and isosceles trapezoid. We're going to put these together because there's only really two differences that make the isosceles more specific. The trapezoid has a pair of opposite sides that are parallel. They are called the bases. It's the top and the bottom. That's true for the isosceles too. But what makes it more specific is an isosceles trapezoid has the left and right sides of equal length that join to the base at equal angles. So we definitely know those are equal angles. With a regular trapezoid, that is not true. So only one pair are opposite, top and bottom. We know those are bases. There are non-parallel sides are called legs, so the ones that are coming at an angle. The length of the mid segment is equal to half the sum of the parallel bases. This is very specific to trapezoid. And then your sum of two consecutive angles is still true here. And your isosceles, this is specific just to the isosceles, not to trapezoids all in a whole. Isosceles has left and right sides of the edges, the legs that we talked about. They're the same length and they join at the same angle, which is shown on the picture. There is our equation. The area is a little different. It's 1/2 sum of the two parallel sides, the top and the bottom bases, times the height. Now let's do an example of just a trapezoid. Given the trapezoid, we just talked about the sum of consecutive angles or adjacent angles is equal to 180 degrees. So we can do x plus 30, which is the left side consecutive angles have to equal 180. And so you minus 30, we get 50. Do the same thing on the right side. Y plus 140 is 180. Minus 140, you get 40. So that was a pretty good one, and it used those consecutive angles pretty well. Now let's try an isosceles triangle. One thing that makes an isosceles trapezoid is that the left and right sides are at equal length and they join to the base at equal angles. So we are given two equal angles at the base. So we can equal those together. 4x equals 2x plus 28. Minus the 2, divide the 2, and you get x equals 14. That is very specific to an isosceles trapezoid. Well, here's all my works cited. Quadrilaterals are super fun, especially these 7. The properties are super quick to learn, and they're super useful to learn. So I'm glad you watched as I went through those properties, and I hope you learned something. Thank you.